Unit 11 Notes Part 3 introduces two concepts, the acid ionization constant and the base ionization constant. For all the problems that we're going to do, we're going to use the acid ionization constant. You can see the basic form here of an acid, and the big thing here is it starts with H and it's A. A can be any anion. So for hydrochloric acid, A would be Cl, so it would be HCl. For sulfuric acid, it would be H2SO4. But more importantly, it's anything with the H out in front. And you're always going to form hydronium and the ion. Ka then is hydronium times A minus over Ha. We leave water out because water is a liquid and has a constant concentration. So we're going to go through a few different types of problems here. The first type of problem is we're going to determine Ka from the pH of a solution. So to do this, we have lactic acid, and it's found in sour milk, and gives us a concentration of lactic acid and a pH of that. We want to know what the ionization constant is. So what we're going to start out with is writing out the equation. So this is just the general form of the equation. In this case, A is lactate, which is the C3H5O3 minus, and we're just going to refer to it as A. You're going to end up having to do an ice chart for this. It says that our lactic acid solution is 0.025. We originally have 0, 0, x, 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 minus x, and 0.025 minus x. So nothing really changes here from what we were doing with equilibrium. The difference here is you are given an extra piece of information, which is pH, which is 2.75. So the pH is 2.75. And we know that pH is the negative log of H3O plus. So if we rearrange this equation to solve for H3O plus, it would be 10 to the negative pH power. So we can do that. We can do 10 to the negative 2.75 power. And that'll give us our concentration of hydronium, which is 0.00178. Now, what that allows us to do is 0.0078, which is hydronium. If you look over here, that's X. So this is 0.00178, this is 0.00178, and this is 0.025 minus 0.00178. So when you do 0.025 minus 0.00178, you get 0.02322322. So now when we solve for Ka, Ka is our products, H3O plus times A minus, so just using the expression from up above on the notes, so 0.00178 squared, because over 0.02322. And when you solve for that, you get 1.36 times 10 to the negative fourth. That's our value for Ka. What our value for Ka tells us is the larger this number gets, it means we formed more products, which means that the acid broke apart more. Another way that we show how much an acid broke apart is to use degree of ionization. And all degree of ionization is, so I'll just call it d of I, it is X, how much you changed in your ice chart, divided by your initial concentration of your acid. So in this case, we changed by 0.00178 because that is what X was, divided by our initial concentration was 0.025 of our acid. And what that tells us is 0.071. Now if we multiply that by 100, it would tell us that 7.1% of our original acid broke apart. And that's really all that it's used for. The next example is going to be the same basic concept, except for this time we're going to calculate the concentrations when we're given Ka. In other words, we're just going to be solving for X. So again, we're given an acid, in this case it's acetic acid, and we have 0.1 molar, so we're going to, again, write out our general form of the equation. We're going to do an ice chart again, and you're going to notice that these ice charts end up all looking exactly the same, so minus x, 0.1 minus x, 0x, x, 0x, x. But now if you look at this one, we end up with our products over reactants, and we know the value for Ka, it's 1.7 times 10 to the negative fifth. So we know Ka, 1.7 times 10 to the negative fifth, equals products, x times x, so x squared, over reactants, 0.1 minus x. This looks daunting because it looks like you're going to end up getting a quadratic. However, with these problems with the acid base, what you can do is take your initial concentration, so initial concentration of your acid, and divide it by your Ka value. If this number is greater than 100, oops, I can't write 100, so we'll write it like this, 100, then we can get rid of this minus x, or if it's a plus x, we can get rid of that. So what that means is take 0.1 divided by 1.7 times 10 to the negative fifth, and it ends up being some big number greater than 100. So what that means is you can just do this. Say bye-bye to that. Now you just have to solve for x. So when you solve for x, you get 0.0013 molar. So our question asks, what's the concentrations of hydrogen ion, which is hydronium, and acetate? It's 0.0013. We solve for x. What is the pH? Well, pH is negative log of H3O plus, and we know H3O plus is 0.0013. So we can solve for that, and it's 2.88. And then the degree of ionization. Well, we take x, 0.0013, and divide it by 0.1, which was our original concentration of our acid, and we get 0.013. And again, if you wanted to percent, you can multiply that by 100, and 1.3% of it would break apart. On the back side, we're going to find one that you end up getting a quadratic for. So we're going to use pyruvic acid. Again, it doesn't matter what acid it is and what the formula is. It's always going to be HA plus H2O gives you H3O plus A minus. You can do an ice chart again. This time you're starting with 0.003 minus x, 0.003 minus x, 0x, x, 0x, x. We know Ka is 1.4 times 10 to the negative fourth. We know it's equal to our products, x times x, or x squared, over our reactants, 0.003 minus x. In this case, though, and I'm just going to kind of do this over here, 0.003 divided by, which is our initial concentration of our acid, divided by Ka, 1.4 times 10 to the negative fourth, is less than 100, meaning we can't get rid of this minus x. So you'd have to go through, you'd have to solve a quadratic. When you do that, you end up getting x equals 0.0005815. I'm rarely ever going to give you a quadratic problem. I've never seen the AP do a quadratic problem using acids and bases. But you could answer the same things here. This is obviously hydronium, so you could solve for pH. You could do degree of ionization in that from here as well. If you look down here, as we scroll down a little bit, there's the base equation right here, and there's Kb. Again, the only difference is a base in a Bronsted-Lowry definition gains an H, so you can see B becomes Hb plus. So then water loses an H, and water acts as an acid here. But same exact process would be done for any of the types of problems. You're just using a base instead of an acid. For polyprotic acids, you have an acid that has more than one hydrogen. And so because it has more than one hydrogen, it has more than one Ka value, because it's going to need a constant each time that it loses an H plus. Since we are going to lose an H plus the first time and then lose it again the second time, you notice that the Ka values that are in this problem down here, 1.3 times 10 to the negative second here, and 6.3 times 10 to the negative 8, there's a big difference between the two of them. So what that means is the hydronium, all the hydronium, in other words, all the pH, comes from the first time breaking apart. The second time only tells us what ion would form. And here's what I mean by that. H2SO3 will break apart into H plus and HSO3 minus when you put that in water. So we'll make that look just like that equation. And then HSO3 minus, when you put that in water, breaks apart to form more H plus and SO3 2 minus. So there are two equations, so you'd end up having to do two ice charts and solve through here. The big thing to know with polyprotic acids is if you are asked for pH, which in this case you are, it says what is the pH, you are only going to use the concentration of hydronium from the first ice chart. Just the same exact ways we were doing up above. Now, the second question here asks, what is the concentration of sulfite ion, SO3 2 minus? this will always equal Ka2. And the reason why that happens is, in the second equation, if you look here, the products of the first equation are H plus and HSO3 minus. Here they're H plus and HSO3 minus. Both of those are going to have the same concentration in the second equation, so they're going to cancel each other out. So Ka is just going to end up equaling SO3 2 minus, always. So those are the only two questions I've ever seen asked, and they're the only things that you're going to be responsible for knowing how to do.